You know, it's funny. In the quiet hours of a crisp autumn morning, you have millions of people worldwide reaching for a steaming cup of coffee.
Yeah.
It is this perfectly mundane, everyday ritual. Like, we don't even think about it.
Right.
But underneath that simple act, they are completely unaware that they are initiating a profound chemical transformation within their own minds. They're literally rewriting their perception with a beverage.
They really are. I mean, we treat it like fuel, right? Like a harmless way to wake up.
Yeah.
But it is fundamentally a psychoactive process. You are ingesting a molecule that crosses the blood-brain barrier and just forcefully alters how your nervous system communicates.
It's wild to think about. And that hidden world, how simple molecular structures dramatically rewrite our cognition, our emotions, our entire internal landscape. That is the core of what we are unpacking today on this deep dive. We are looking at the actual mechanics of psychopharmacology. And for our sources today, we're diving into Susan Barron's really comprehensive chapter from the NOBA Discovering Psychology textbook. And we're layering that with a set of lecture notes from Dr. Riordon's intro psychology classes.
Yeah, and the underlying goal here, the real mission of this deep dive, is to bridge the massive gap between pure biology and human empathy.
Right.
We're trying to look past the visible symptoms of behavior to understand the molecular battles happening silently inside our heads.
Because it's so easy to just see the behavior, right?
Exactly, because when you grasp those microscopic mechanics, you finally start to see why a drug that miraculously saves one person can push another person into a profound medical crisis.
Okay, let's unpack this, because to really understand how these chemicals change us, we have to start by zooming way, way in.
Right, down to the cells.
Yeah, we are looking at the brain's 86 billion neurons. And reading through Dr. Riordon's notes, the absolute wildest detail to me is that these 86 billion neurons, this massive electrical grid inside our skulls, they never actually touch each other.
No, they don't. It completely defies how we usually visualize biological wiring.
Yeah, like you'd think it's all connected.
Right. If you look at the nervous system, it's not a closed loop of continuous copper wire like the electrical system in your house.
Okay.
The neurons, they have to exchange vital messages across these microscopic cellular gaps, which are called synapses.
So they are essentially shouting across a canyon, hoping the message gets heard on the other side.
A canyon is everything. It really is.
Yeah.
Communication only happens when a sending cell releases specific chemical messengers, neurotransmitters, into that void.
Okay, so the chemicals get released.
Yeah, and those molecules just drift across the microscopic gap and physically bind onto specialized receptor proteins on the receiving cell. And that single fragile mechanism regulates absolutely everything you experience. Basic physical movement, your heart rate, your deepest emotional states. All of it depends on molecules floating across a gap.
So when someone introduces a psychoactive drug into the mix, whether that caffeine from your morning coffee or a powerful antidepressant, they are intentionally throwing a chemical wrench into that delicate microscopic dam.
They are flooding the canyon.
Yeah.
That's what they're doing. Drugs primarily manipulate this communication process via two main mechanisms. They act as either agonists or antagonists.
Okay, break that down for me.
So you can think of agonists as amplifiers. They are structurally similar enough to our natural neurotransmitters that they can bind to those receptors and actively mimic or boost the signal.
Oh, I see.
Yeah, they artificially turn up the volume of the brain's internal messaging system.
And then antagonists would be the silencers, right?
Exactly.
But they aren't just turning down the volume, are they? From the reading, it seems more like they are aggressively blocking the signal entirely.
They are physically occupying the parking space.
Oh, okay.
Yeah, an antagonist binds to the receptor site on the receiving cell, but it doesn't activate it. It just sits there, barricading the door so the natural chemicals have nowhere to connect. It effectively shuts down specific neural conversations.
But reading through the materials, it becomes incredibly clear that no drug acts with absolute laser-targeted perfection. I think we have this modern expectation that a pill is like this magic bullet.
Right, that it goes straight to the problem.
Yeah, straight to the problem area and fixes it.
And that expectation completely ignores the reality of chemical overflow.
Okay.
When you ingest a chemical, it doesn't have a GPS system directing it to the one specific synapse causing your anxiety or your tremor.
It just goes everywhere.
It washes over the entire central nervous system.
Burrow.
The medication inevitably spills over onto unintended neural pathways. And this triggers a wide array of problematic bodily reactions, which we just casualize with the term side effects.
Let me see if I can picture this. Is this kind of like trying to water a single specific house plant in your living room, but all you have is a massive high-pressure fire hose?
Yes, that captures the collateral damage perfectly.
You might get the plant watered, but you are inevitably going to destroy the drywall and completely flood the carpet in the process.
Exactly. And that fire hose effect explains a really tragic clinical reality. Patients frequently find themselves taking supplementary pills just to tolerate the collateral damage of their primary prescriptions.
Oh, man.
Yeah, like someone takes a pill for their mood, but that chemical overflow hits the pathways regulating sleep, causing severe insomnia.
So they can't sleep because of the mood pill.
Right. So they take a second pill to force themselves to sleep, which leaves them profoundly groggy the next day.
Mm.
Then they start leaning on stimulants just to function.
It's just a domino effect.
It is. Eventually, the physiological burden becomes so exhausting that individuals just abandon their treatment plans entirely.
To make that whole fire hose scenario even more precarious, the houseplant itself, like our actual biology is constantly changing as we get older. You brought in Turnheim's study from 2003 on this, and that completely changed how I view medication dosing.
Yeah, Turnheim's research is fascinating. It focuses on how the physical shape and responsiveness of those neural receptors degrade and alter as we age.
So the receptors literally change shape.
Yes, the receiving hardware on the other side of the synapse becomes fundamentally different.
Wow.
And this carries massive real-world implications, particularly in modern academic or workplace environments where you have older, non-traditional learners balancing heavy cognitive loads with complex prescription regimens.
So a dose that turns up the volume perfectly for an 18-year-old might be completely overwhelming for a 40-year-old, even if they are taking the exact same pill for the exact same condition.
Exactly. The subtle changes in neuroreceptor binding mean the older nervous system often experiences a highly magnified sensitivity to cognitive side effects. A mild focus aid for a younger person can trigger severe memory impairment or deep lethargy in an older adult, simply because the microscopic locks on their cells have changed shape over decades.
But wait, if the receptors themselves are that sensitive and the overflow effect is that delicate, then the physical way the drug enters our body must matter just as much as what the drug actually is.
Oh, the physical journey is everything. In pharmacokinetics, the threat level of a compound is entirely dictated by the path it takes to reach the brain.
Right.
We often just call this speed, but it's really about the biological gauntlet the molecule has to survive.
Swallowing a pill, the oral route, is the slow path. And the textbook notes this is highly unpredictable because it's not a direct line.
Not at all.
Yeah.
When you swallow a pill, you force that compound through a brutal digestive gauntlet.
Yeah.
The actual amount of active chemical that eventually reaches your bloodstream is constantly being altered by the acidity of your stomach, the presence of fat molecules from your last meal, and just your general digestive transit time. It's a winding, erratic road.
Then you look at the rapid paths, like intravenous injection or direct inhalation. Those methods completely bypass the digestive system.
Right.
The sources note they can deliver active molecules directly to neural tissue in under 10 seconds.
10 seconds from ingestion to a complete chemical rewrite of your brain.
That's terrifying.
It is. And that vanishingly small window of time is the core biological driver of addiction. When a substance triggers the brain's internal reward pathways, it completely hijacks the reward center.
Because there's no delay for the brain to process what's happening. It just goes, I performed this action and the reward was instantaneous.
Exactly. The brain is an association machine. When the chemical rush happens in under 10 seconds, the mind builds an incredibly powerful, unbreakable link between the intense euphoria and whatever ordinary setting you happen to be in.
So we are basically talking about classical conditioning, right?
Yeah.
Like Pavlov's dogs salivating at the sound of a bell, but on a much, much more intense scale.
It is the exact same mechanism. If a person is using a rapid delivery drug in a specific dorm room or hanging out on a particular street corner, the brain weaves that visual and spatial data into the addiction profile.
Wow.
Those ordinary objects become hardwired as environmental cues.
This makes the Lopez study from 2015 on methamphetamine cravings make so much sense.
Yes.
They found that rapid administration creates vastly stronger automatic cravings when a person is exposed to those environmental cues compared to people who used slower methods.
It perfectly explains the devastating phenomenon of sudden relapse. A student can go to rehab, detox successfully, and feel entirely in control.
Right.
But the moment they step back onto their college campus and simply walk past that specific building, they are hit with a physical wall of craving they cannot control.
Let me stop you there because the implication of that is just terrifying to me. Are you saying the physical architecture of a building, just the sight of a brick wall or a dorm door, can trigger actual biological withdrawal cravings independent of the drug itself?
Yes, the brain's classical conditioning is that profound. The building itself becomes the biological trigger.
Oh my God.
It's an automatic, unconscious physiological reaction built entirely by that under 10-second delivery speed. Gabor Mate described this dynamic so powerfully when he wrote, "Addiction is a modern disease, born of a culture that isolates us and commercializes our desires. The environment itself becomes an active component of the disease."
That feels incredibly fatalistic, but the Lopez study did offer a counterweight to that, pointing out that we aren't just slaves to our conditioning, right?
Right, they demonstrated that human cognition can still intervene. By teaching targeted cognitive behavioral strategies, individuals can actively reclaim control over how they process those visual triggers.
Oh, okay, so there is hope.
Yes, it requires immense, exhausting effort to consciously override that rapid-fire conditioning. But patients can essentially rewrite their biological reaction to building. The mind can push back against the chemistry.
Well, if the rapid routes bypass the body's defenses, let's look closer at those defenses on the slow route. When you do swallow a pill, the drugs have to get past the body's primary chemical purification facility, which is the liver.
The liver really is the unsung hero of pharmacokinetics.
Yeah.
It is packed with specialized protein molecules called enzymes, whose entire job is to dismantle foreign substances. And the most crucial players here belong to a large family of proteins known as the cytochrome P450 superfamily.
Cytochrome P450. It sounds like a droid from Star Wars, but it's really more like a microscopic disassembly line.
That's a good way to put it. When operating normally, those P450 enzymes steadily pull apart the active compounds in mind-altering prescriptions. They are the conveyor belt, ensuring that foreign chemicals are broken down and safely exit the body before they can cause internal damage.
Here's where it gets really interesting, because that disassembly line is surprisingly fragile.
It is.
The textbook drops a massive bombshell about a very common breakfast item that completely jams the gears: grapefruit.
Oh yeah. It remains one of the most dangerous and poorly understood dietary interactions in everyday medicine.
It's just juice.
Right. But grapefruit juice contains active natural compounds that physically bind to and neutralize specific cytochrome P450 enzymes inside the liver.
So eating a healthy snack like grapefruit is basically stripping your liver's security guards of their weapons, letting all the chemicals just rush the gates.
It essentially unplugs the conveyor belt.
Unbelievable.
The medication loses its primary exit route. The drug is still entering the bloodstream, but the biological machinery required to break it down has been temporarily shut off.
Okay.
As a direct result, standard doctor-prescribed doses unexpectedly accumulate into severely high, toxic concentrations.
And Bressler's 2006 clinical review highlighted that this isn't just a brief hiccup in digestion either.
No, not at all.
These elevated toxic chemical levels can linger in the human body for days after drinking just a single glass of juice.
Days. It affects dozens of common psychiatric drugs. Medications for bipolar disorder, severe anxiety, obsessive-compulsive disorder. Put yourself in the shoes of a college student during a brutal finals week.
Okay.
They are exhausted, they take their prescribed anti-anxiety medication, and they wash it down with a glass of grapefruit juice, genuinely thinking they're making a healthy choice to get some vitamin C.
And instead, they unknowingly trigger profound confusion and severe dizziness because they've just given themselves a toxic overdose of their own medication.
Exactly.
For a traditional student, that might mean failing an exam. But for a non-traditional student who has to commute on a highway to a full-time job or operate workplace machinery, that sudden spike in drug levels is a catastrophic impairment.
It's incredibly dangerous.
It's not just breakfast that jams the disassembly line, though. The sources make it clear that the blueprint of the factory itself, our unique DNA, fundamentally wires how that liver operates. This makes standard one-size-fits-all prescribing incredibly risky.
Welcome to the genetic lottery of psychopharmacology.
Yeah.
The global human population actually divides into 4 distinct metabolic categories, purely based on how rapidly our specific genetic sequence tells those liver enzymes to process foreign chemicals.
Which perfectly explains why treating severe depression currently requires 4 to 6 agonizing weeks of blind trial and error.
It's a nightmare for patients. A patient walks into a clinic desperate for help. They are prescribed a standard dose of an antidepressant. They wait a month and a half, enduring all their original symptoms, only to find out the medication doesn't work.
That's just crushing.
It is. The NOBA chapter explains the mechanics of why this happens. They might fall into the category of an ultra-extensive metabolizer.
Let me get this straight. If I'm an ultra-extensive metabolizer, am I practically immune to standard doses? I could be taking a pill every day for a month that is literally doing zero for my brain.
Yes. Your liver enzymes are working so aggressively that the standard dose is dismantled before it ever achieves therapeutic levels in your brain. You get zero relief, completely dictated by your DNA.
But the flip side of that coin is just as bad. You have poor metabolizers.
Their enzymatic conveyor belt moves at a snail's pace.
Okay.
For a poor metabolizer, a standard dose creates a severe bottleneck. The chemicals accumulate to highly toxic levels, meaning the patient experiences all the severe side effects without any of the intended psychiatric relief.
Standard prescribing starts to look a lot like a doctor throwing darts at a biological dartboard while blindfolded.
That's unfortunately accurate.
But the APA Division 55 publication from 2022 outlines a tangible solution to this, right? Pre-treatment DNA testing.
It represents the end of the guessing game in psychiatry. By analyzing a simple blood or saliva sample before writing a single prescription, a clinician can instantly map a patient's exact metabolic profile on day one.
That's incredible.
They can practice truly personalized medicine, customizing the dosage to bypass side effects and maximize therapeutic benefits immediately.
They noted this is especially vital for students who frequently drop out of their education entirely out of frustration with months of medical experimentation. I mean, a single parent trying to get their degree while battling severe depression literally does not have 6 weeks to wait and see if a pill might work.
If we connect this to the bigger picture, the legendary physician William Osler summarized this philosophy perfectly over a century ago. He said, "It is much more important to know what sort of a patient has a disease than what sort of a disease a patient has."
Wow. The biological blueprint of the patient determines the entire outcome.
Exactly.
But even if we map that DNA flawlessly and we rigorously avoid grapefruit juice, we are still applying these powerful chemicals to chaotic, vulnerable human lives. This brings us to the final piece of Dr. Riordon's lecture notes, which focuses heavily on macro populations and the absolute necessity of empathy in medicine. Because human beings are not static laboratory models, we have to examine how these drugs affect the extremes of age.
The pediatric dilemma is particularly alarming. The sources cite a staggering statistic: a 40-fold explosion in childhood bipolar diagnoses over a single decade.
A 40-fold spike. That means we are prescribing powerful psychotropic drugs to young kids at an unprecedented rate. But the ethical dilemma the textbook points out is that most of these psychiatric medications have only ever been rigorously tested on young, healthy adults.
The long-term safety data for pediatric populations is incredibly scarce. The human brain is not fully baked at age 10.
No.
It undergoes complex foundational structural development until a person is well past 20 years of age. Introducing powerful mind-altering chemicals into a rapidly growing neurological framework risks unpredictable, lifelong changes to that hardware.
You are pouring concrete while the foundation is still being dug.
Exactly.
It makes complete sense why the authoritative 2008 APA report aggressively urged clinicians to lean heavily on psychosocial therapies first for young populations, rather than jumping straight into unvalidated prescription practices.
And the biological complexities don't vanish when we get older. The hazards just shift. At the opposite end of the lifespan, the elderly face an entirely different set of perils. As we saw with Hernheim's study, the aging process drastically slows natural liver metabolism.
The P450 enzymes get sluggish, the conveyor belt grinds down.
Combine that sluggish metabolism with the reality of polypharmacy, the concurrent use of multiple daily medications to treat various co-occurring illnesses.
Right.
An older patient might be taking heart medication, blood pressure pills, diabetes meds, alongside a psychiatric prescription.
Because the metabolism is moving so slowly, these standard adult doses start backing up and stacking on top of each other in the bloodstream.
The chemical accumulation is rapid and severe. In elderly patients, this frequently manifests as profound dizziness, which inevitably results in dangerous falls.
Oh, that's terrible.
For an older individual, a fall often shatters fragile bone tissue, initiating a cascade of physical catastrophes that they may never recover from. all of it stemming from a standard medication dose that wasn't properly adjusted for an aging metabolism.
This entire disconnect between pure science and human reality culminates in a simulation Dr. Riordon uses in their lecture to teach medication adherence. It is conceptually simple, but it sounds incredibly stressful.
Oh, it's brilliant. Students are given a rigorous HIV treatment protocol to simulate over a period of time. But instead of real antiretroviral drugs, they're given packets of Kool-Aid and Tic Tac mints.
They have to follow the exact unforgiving timing, the strict dietary restrictions, and the complex dosage schedules of a real patient.
Right.
And they have to do this while just trying to live their normal lives, going to class, working part-time jobs, studying.
The lesson hits them very quickly. You can have the most flawlessly engineered pharmacology in the world, but it fails completely if a patient cannot navigate the behavioral, environmental, and psychosocial barriers to actually swallowing the pill at the right time.
Does the perfect pharmacological cure even matter if we completely ignore the chaotic reality of a human being's daily life? I mean, imagine you are running late for a crucial chemistry lab. Your boss at your part-time job just changed your shift, and you realize you forgot your Tic Tacs back at the dorm.
This raises an important question. The physician and author Jerome Groopman captured this limitation beautifully. He wrote, "The clinical trial is a blunt instrument used to find truths that apply to an abstract average person, not the unique individual standing before you."
I can't think of a better synthesis for this entire deep dive.
Yeah.
We started with 86 billion neurons firing chemical messengers across microscopic canyons. We looked at how the physical gauntlet a drug survives, whether it's a slow digestive crawl or a rapid 10-second injection can hijack our environment and hardwire addiction to a book wall. We uncovered the hidden, lingering danger of a single glass of grapefruit juice, unplugging our liver enzymes. We saw how DNA screening could end the agonizing trial and error of depression treatment. And finally, we realized that without deep human empathy, without considering the developing brain of a child or the chaotic daily life of a student managing Tic Tacs in a simulation, the pure science falls completely flat.
It is a massive journey, from the microscopic molecule to the macro reality of human behavior. But looking closely at the biological realities we covered today, I want to leave you with one final thought to mull over.
Okay.
We noted very clearly that the human brain undergoes complex structural development until age 20. And we also explored how the aging process fundamentally alters neural receptor sensitivity and slows our liver enzymes later in life.
The biological hardware is in a constant state of flux.
Exactly. So here's the fascinating question to take away. Considering all of that change, is there ever truly a stable window for psychopharmacology in the human lifespan? Or is prescribing medication to the human brain always going to be aiming at a constantly moving biological target?
So what does this all mean? A constantly moving target. Something to think about tomorrow morning when you reach for that steaming cup of coffee and initiate your very own profound chemical transformation.